In the previous video, we studied two concepts. The first was the directional derivative of f at the point C along the direction x. And this was defined to be equal to limit epsilon tends to 0 f of c plus epsilon x minus f of c whole divided by epsilon. We further saw that if f is differentiable, then this quantity is equal to a dot x, where a is the special vector given in the definition of differentiability. And it was later observed that this a is equal to the gradient of f. And gradient of f was the second concept that we learned in the previous video. Gradient of f was defined to be equal to del f by del x1, comma del f by del x2, etc. up to del f by del xn. Let us also recall what we meant by del f by del xi. Del f by del xi at a point C is equal to the directional derivative of f at the point C along the direction ei. And this is true for all I. Therefore, if the function f is differentiable at the point C, then the directional derivatives are determined by the gradient. If f is not differentiable, we cannot guarantee it. Let us look at an example of this phenomenon next. Consider the function f from R2 to R defined as f of x comma y is equal to y if x is not equal to 0 and 0 if x is equal to 0. Let us calculate the partial derivatives of this function. That is, let us look at del f by del x at 0, 0, which is equal to the directional derivative of f at the point 0, 0 along the direction 1, 0. This is equal to limit epsilon tends to 0 f of epsilon comma 0 minus f of 0 comma 0 whole divided by epsilon. But notice that f of epsilon comma 0 is equal to 0 as y is equal to 0 and f of 0 comma 0 is equal to 0 as x is equal to 0. Therefore, the limit is equal to 0. Similarly, we can find the partial derivative with respect to y, which is equal to the directional derivative along the direction 0, 1. Now we know that this is equal to limit epsilon tends to 0 f of 0, epsilon minus f of 0, 0 divided by epsilon. As the x coordinate is 0 in 0, epsilon and 0, 0, both the terms in the numerator are 0. Therefore, the limit is again equal to 0. Thus, we can see that both the partial derivatives are equal to 0. That is, the gradient is the vector 0, 0. We will next observe that even though the gradient is 0, 0, some of the directional derivatives are not equal to 0. Take an arbitrary point a, b in R2 where a and b are both given to be non-zero. Then we will try to find the directional derivative of f at the point 0, 0 along the direction a, b. We know that this is equal to limit epsilon tends to 0 f of a epsilon, b epsilon minus f of 0, 0 whole divided by epsilon. As a epsilon is non-zero, f of a epsilon, b epsilon will be equal to b epsilon. Therefore, we get limit epsilon tends to 0 b epsilon by epsilon, which is equal to b. On the other hand, if you look at the gradient of f at 0, 0 dot a, b, as gradient of f at 0, 0 is equal to 0, 0, we get 0, 0 dot a, b, which is equal to 0. Thus, we see that these two are not equal. And this happened because the function f was not differentiable. In the assignments and homeworks, we have seen examples of functions such that all the directional derivatives exist, but the function is not even continuous, and therefore it cannot be differentiable as well. We have also seen examples where the function is continuous, all directional derivatives exist, but still the function is not differentiable. This function is yet another example of this phenomenon. You can show that this function is continuous at all points, however is not differentiable at the origin. I leave the proof of these two facts as an exercise. Anyways, as long as f is differentiable, we can say that the directional derivative of f at the point C along the direction x is equal to the gradient of f at C dot x. Therefore, the norm of this is equal to the norm of this, which is less than or equal to norm of gradient of f at C into norm of x by the Cauchy-Schwarz inequality. And if you recall the proof of the Cauchy-Schwarz inequality, you will remember that the basic idea was that given two vectors x and y, you can represent norm x square as norm of x minus x dot y by y dot y into y the whole square plus x dot y by y dot y the whole square into norm y square. Then we observed that this quantity is always greater than or equal to 0. Therefore, this will be less than or equal to this. And then we did some jugglery. Therefore, the inequality will become an equality if and only if this is equal to 0. And recall that a norm of a vector is 0 if and only if the vector is 0. That is, x is equal to the component of x along y. In other words, x is a scalar multiple of y. That's what it means. That is, this inequality will become an equality if and only if grad f and x are scalar multiples of each other. Let us repeat. The norm of the directional derivative of f at the point C along the direction x is equal to the norm of the gradient of f at C into norm of x if and only if x is equal to alpha times grad f at C. In other words, the equality holds if and only if x lies along the gradient of f. Further, if we are assuming that we are taking directional derivatives along unit vectors, then we can ignore norm of x. And we can say that norm of directional derivative of f at C along the direction x is less than or equal to the gradient of f at C. And it will be equal to gradient of f at C if and only if x lies along gradient of f. Thus, the vector grad f of C is a vector whose direction gives us the direction of maximum change and its magnitude gives us the change in that direction. And this is the geometric significance of gradient.